Hello students, welcome to engineering chemistry class, lesson 7, crystal field splitting in octahedral complexes. Today we are going to apply the crystal field theory or the crystal field postulates in the octahedral complexes. How splitting of d orbitals in octahedral complexes take place. In an octahedral complex, the central metal atom or central metal ion is surrounded by 6 lone pair of electrons. As the ligand approach to the central metal ion, the degeneracy of d orbital of the central metal ion will be removed by the repulsion between the electrons of metal and the electrons of ligands. The approach of ligands is considered as two process. It is a two-step process. In the first step, it is assumed that the ligands approach the central metal ion spherically, that is at an equal distance from each of the d orbitals. At this stage, all the d orbitals are increased in energy by the same amount. The 5d orbitals remain degenerate. In the second step, the spherical field changes to octahedral field, leading to the splitting of d orbitals. So the energy of d orbitals splitted between Eg are nothing but Eg are dx square minus y square and dz square, and T2G sets are dxy, dyz, dxz due to the approach of ligands along the axis. The energy of Eg is greater than T2G because there is more repulsion in Eg due to the approach of ligands along the axis. And in this slide, you can observe the energy difference between T2G and Eg orbitals is nothing but the crystal field splitting, and it is denoted by the symbol del O. You should not pronounce it as delta naught. It is del O, octahedral, or 10 dq. So, under the influence of ligands, the d orbital split into T2G with less energy and another as Eg with lower energy. Sorry, Eg with higher energy. The main energy level between these two sets of orbitals is 0. This is nothing but a Barry's center. The magnitude of stabilization will be 0.4 del O or 2 by 5 del O. Here why 2 by 5? Because the 2 represents the two orbitals splitted away from T2G. So that is represented by 2 by 5, and the magnitude of these stabilization will be 0.6 del O. Here 2 orbitals lower to the T2G set of orbitals. And this is the formula to calculate the crystal field splitting energy for high spin and low spin complexes. If the ligand is weak field, then we will get high spin complex. The formula is shown here: minus 0.4 P plus 0.6 Q into del O, where P is the number of electrons in T2G set of orbitals and Q is the number of electrons in E2G or EG orbitals. And the formula to find out the crystal field splitting energy for low spin complexes are low spin complexes is minus 0.4 P plus 0.6 Q del O plus MP, where P is the number of electrons in T2G set of orbitals, Q is the number of electrons in E2G set of orbitals, and M is the number of pair of electrons caused by the ligands, and P is the capital P is the pairing energy. Now comes a reflections part. Students, try to calculate the crystal field splitting energy for the complexes D4 and D6 high spin complexes using the formula given here. For high spin complexes, you have to use minus 0.4 T plus 0.6 Q delta naught. Here the ligands you take for high spin complexes means it is a weak field ligand. So use this formula to calculate D4 and D6 CFSE. After calculating the CFSE, resume the video. I'm going to give you the answers. Yes, the answers is displayed here. The answers are displayed here. The electron arrangement and CFSE for octahedral complexes for all the d orbitals are shown here from D1 to D10. First, strong field and a weak field ligand CFSE is displayed. For high spin D4, it is the CFSE is 6 dq or minus 0.6 del O. For high spin D6 complex, it is 4 dq or 0.4 del O. You can check, you can calculate by your own for the other orbitals also from D1 to D10 for low spin and high spin complexes. You can calculate. I hope you understand this topic very well. Thank you, students. Thank you for listening.